All right, so this is a quick little video about operations with complex numbers. This should be review from Integrated 2, but I don't know how much you saw of it last year, so you might have forgotten a lot of it. But the good news is it's not that bad. But remember, complex numbers come from combining real and imaginary numbers, and imaginary numbers come from this problem of what the heck is the square root of -1? We know how square roots work, that whatever the answer is, we should be able to multiply it by itself and get -1 for an answer. But the answer can't be positive because a positive times a positive won't be negative. It can't be negative because a negative times a negative won't be negative. It can't be 0 because 0 times 0 is not negative, so no real number worked, therefore it must be imaginary. So the square root of -1 became defined as the imaginary number I. And if that's true, then that means I times I is -1. Now, just a quick couple of little things. Number one is we call these imaginary numbers, and I know that makes a lot of people wonder, like, why the heck are we learning these then? If they're imaginary, what do they have to do with anything? And it's actually just a bad name. They actually do have a lot of real-life applications in physics. So just because we call them imaginary doesn't mean these numbers don't have real world applications. So I just want to make that clear. The other thing is a lot of students get confused and say that I must equal -1. And remember, that's not true. I is equal to the square root of -1. And that means I times I is -1. But I by itself is not -1. So just don't get that mixed up. Okay, so now that we got that out of the way, let's talk about our operations. So the first one is just, excuse me, powers of I. And so powers of I, like I to the first power, I to the second, I to the third, I to the fourth, and so on. And it turns out there's a nice pattern. We know anything to the first power is itself. And then we've also defined up here I times I, which is the same thing as I squared, to be -1. And then I've worked out some of the other ones here, the next one. So I cubed means you're multiplying 3 i's, and I times I is -1. And then we have an I, and -1 times I is -I. So I cubed is -I. And then if we have I to the fourth power, that means you're multiplying 4 i's. So one way to look at this is you multiply a pair of i's, you get -1. Another pair of i's, you get -1. And -1 times -1 is 1. So I to the fourth power is 1. And one last one, I to the fifth power, you're multiplying 5 i's. But we just showed over here that when you multiply 4 of them, you get 1. So if we multiply by 1 more I, we're going to get I. And then it's just going to start repeating itself. So to find I to the power of any number, you find which one of the first 4 in this list right here it's equivalent to. And how do you do that? It's actually a pretty easy thing. So if we take a look at I to the power 50, I mean, we could list out 50 i's, but that sounds awful. So instead of doing that, because it's going to repeat every 4 times, let's take 50 divided by 4, and we're going to get a remainder of 2. That remainder becomes your new exponent. So I to the power of 50 is the same thing as I squared, which in the list above is -1. If we look at I to the power of 12, 4 goes into 12 with no remainder, so it's I to the power of 0, and anything to the power of 0 is 1. And 4 goes into 23 with a remainder of 3, so we can just look at I cubed, which is -I. And then even if we combine things, remember we can't do a shortcut of combining exponents, but we can work these out individually. I to the 15th power is the same thing as I cubed, which is -I. I to the 29th power is the same thing as I to the first power, which is I. And -I, or minus I, is -2i. So there you go, there's powers of I. So now the next operation. Oh, wait, sorry. Before we look at the next operation, let's just talk about complex numbers super quickly. So complex numbers are when you take a real and an imaginary number and put them together. We can't really add these together. They're not like terms. And I know this looks like a problem, a plus bi, but it actually isn't a problem to work out. It's a number. We call it a complex number. This is one number by itself, so that's a little weird. The other thing is the standard form for a complex number is a plus bi. And you must put the real number before the imaginary part. So you're going to see for the rest of the problems now, when I'm writing my answer, it's always going to be in standard form. The real part and then the imaginary part. Okay, so let's do some operations now. Let's look at addition and subtraction. Good news is this is just like combining like terms. So look at this example. We have this one complex number, 4 minus 2i, and we're going to add this complex number, 7 minus I. Just combine your like terms. 4 plus 7 is 11, and negative 2i minus I is negative 3i. And again, you put the real and then the imaginary part, a plus bi. That's it. Even if you have a longer problem like this with some subtraction and addition, just don't forget that subtraction sign is going to distribute. So a negative times a 7 is negative 7, and a negative times a negative 2i is positive 2i. But after that, combine your like terms. 3 plus negative 7 is negative 4, and negative I plus 2i plus 3i is 4i. And again, the real plus the imaginary. And that's it. So addition and subtraction, super easy. The next one is multiplication, and that's not much harder. It's just a couple more steps. But the good news is it's very similar to working with variables again. So if I have 3 minus 2i times 4 plus I, be careful, a lot of students will mix up the addition with the multiplication. So there's no operation here. It's implied multiplication. So I just set up the boxes just like we would if that was an x. So 3 minus 2i and 4 plus I, and just multiply. 3 times 4 is 12. Negative 2i times 4 is negative 8i. 3 times I is 3i. And negative 2i times I is negative 2i squared. And then, like normal, we have our like terms here. So negative 8i plus 3i is negative 5i. But there we go. So this first line is just like it was if it was a variable x. But we can go a little further because it's not a variable. I is actually a number, and we can work with this I squared. Remember, I squared is the same thing as negative 1. And then negative 2 times negative 1 is positive 2. And then we can combine our like terms and get our final answer here of 14 minus 5i. Again, a plus bi. Make sure you put it in standard form. So that's the only thing with multiplication. You just can go a little further. It starts out just like it was a variable, but then you're going to get this I squared, which is negative 1. So just simplify all the way. So here's another problem. There's no new trick. It really is the same exact thing. So here's 7 minus 5i right there. And then 6 plus 2i is right there. And then again, just multiplying to get what goes inside all these boxes. I combined like terms here to get the negative 16i. And now we'll work with the I squared. I squared is negative 1. Negative 10 times negative 1 is positive 10. Combine your like terms, and there's your answer in standard form. So multiplication, not too bad either. Then we get to division. Division isn't bad, it's just not as intuitive. The other ones make sense. This one's just weird. So if we're going to divide complex numbers, so this is the weird operation, because we don't actually divide. I mean, sometimes we do at the end, but it just kind of depends. But here's division right here. It's 5 divided by 7 plus I. And we want to be able to write it in the form a plus bi. And this is not, the whole fraction is not in the form a plus bi. And believe it or not, it's going to help if we can get rid of the I. If we can cancel the I in the denominator somehow, we'll be able to do this. And you'll see at the end how getting rid of the I will help us. But right now, we have this I in there. We're kind of stuck. So let's see what we do. The trick is right here in green. Multiply top and bottom by the conjugate of the bottom. So what do I mean by that? If you don't remember what a conjugate is, don't worry, that's a super easy idea. You just change the operation. So if it says 7 plus I, its conjugate is 7 minus I. If it's a plus sign here, you make it a minus. If it's a minus sign here, you make it a plus. Notice the 7 is not changing signs. So if it was a negative, it would stay a negative 7. It's a positive 7, it's staying a positive 7. It's just the operation in the middle. But I have to multiply top and bottom by the same thing. Remember that giant 1 that you learned about in integrated 1. So I have to multiply by a form of 1 so I don't change the value. So again, this is the thing you got to remember with division. The trick is multiply the top and the bottom by the conjugate of the bottom. So let's see what happens. How does this help us? So the top is easy. Like if we just go top times top, it's just a simple distribution and we get this. In the bottom, you actually have to multiply these complex numbers together. So let's look at what happens when you multiply them in the boxes. 7 times 7 is 49. I times 7 is 7i. 7 times negative I is negative 7i. And I times negative I is negative I squared. But look what happens when we combine our like terms. There's a positive 7i and a negative 7i. They're just going to cancel each other out. And that's always going to happen when you multiply conjugates together. And it makes sense, because conjugates are the exact same thing, we just have a different sign in the middle. And so when we multiply, it makes sense that our like terms in the middle are just opposites of each other. They're the same thing, just with opposite signs. So they're going to cancel. So all we're left with is the 49 minus I squared. And then again, we know I squared is negative 1, and 49 minus negative 1 is 50. So by multiplying by the conjugate, we were able to get a real number in the denominator. And that's the key. By getting a real number in the denominator, then we can do a simple little division here, put each one of the terms in the numerator over the denominator, and then just reduce each fraction, and we get that as our answer. So the key to getting rid of the I, so we can get a real number in the bottom, so that way we can divide by the bottom and then get A plus BI. So we'll do one more of these, and that'll be the end of the notes today. So here's our last example. So we have 4 minus I divided by 3 plus 2i. So again, how do we do this? We're going to take this and multiply by the conjugate of the bottom. So it was 3 plus 2i, the conjugate is 3 minus 2i. Again, we multiply the top and the bottom by that. Now, unfortunately, when we multiply the tops together, it's not like the previous problem. We're going to have to go ahead and set up boxes, or just make sure we fully distribute. The 4 gets multiplied by each thing and the negative I gets multiplied. But that's what I did over here, set up the boxes. So there's 4 minus I and 3 minus 2i. And then I got the things in the boxes. When I combine the like terms, negative 3i minus 8i, that's negative 11i. And then I just went ahead and combined these also. I did this part kind of in my head. So we know I squared is negative 1. Negative 1 times 2 is negative 2. So 12 plus negative 2 is 10. So that's where this numerator came from. Now in the denominator, I didn't show any box. There's no box. And that's because I know that these are going to cancel out when I multiply conjugates. So I just took the shortcut. First times first, 3 times 3 is 9. And last times last, 2i times negative 2i is negative 4i squared. You can always do the boxes if you want, if you forget the shortcut for doing conjugates, but I'll tell you, it'll really help if you can get that down with multiplying conjugates that just do first times first and last times last, because it shows up a lot. But then, I just kind of went further with it. I squared is negative 1, so this becomes a plus 4. 9 plus 4 is 13. And then divide each term in the top by 13, and in this case the fractions don't reduce, so there's my answer. So again, it's not too much work, at least. Just division is it's the one that's not intuitive. You really do have to remember what the method is for that. So there you go. There's operations with complex numbers. Have fun.